Imagine standing under the night sky, gazing at the stars, when suddenly an invisible bullet streaks through your body at nearly the speed of light. You don't feel it. You don't see it, but it's there, a cosmic ray, one of the universe's most elusive and mysterious travelers. These high-energy particles, born in the depths of space, have been piercing through Earth and through you for billions of years, carrying secrets we're only beginning to unravel. Some come from exploding stars, others from black holes or distant galaxies, but the most enigmatic ones, their origins remain a total mystery, defying even our most advanced science. What if I told you that some of these cosmic rays pack so much energy, a single particle can rival a major league fastball, or that others arrive in patterns so strange, they've left scientists debating whether they're messages from an unknown cosmic phenomenon. These aren't just random bits of space debris, they're cosmic puzzles, each with its own story, its own riddles waiting to be solved. From the infamous "oh my god" particle, which shattered every expectation of physics, to bizarre rays that seem to appear and vanish without explanation, the universe is sending us clues wrapped in pure energy. And the deeper we look, the more questions we uncover. Today, we're embarking on a journey through the top 25 most enigmatic cosmic rays ever detected, particles so extraordinary they've rewritten textbooks and sparked entirely new fields of study. We'll explore the ones that shouldn't exist, the ones that point to gaps in our understanding of the cosmos, and the ones that might just hold the key to unlocking the universe's greatest secrets. This isn't just a list, it's a detective story, a hunt for answers in a universe that loves to keep us guessing. So, are you ready to dive into the invisible, high-energy marvels that shape the very fabric of reality? Let's begin. Picture this: October 15, 1991, over the desert skies of Utah. A cosmic ray detector named the Fly's Eye catches something impossible. A single subatomic particle hurtling toward Earth with the energy of a brick dropped from waist height. But here's the catch. This particle was moving at 99.9999999999998% of the speed of light. Scientists were so stunned, they named it the "oh my god" particle. To put that in perspective, its energy was 320 exa-electron volts, millions of times more powerful than anything our most advanced particle accelerators can produce. It hit with the force of a major league fastball, all packed into something smaller than an atom. So where did it come from? That's the real mystery. Even our most violent cosmic events, supernovas, neutron star collisions, shouldn't be able to accelerate particles to this energy. Theoreticians scrambled. Some pointed to supermassive black holes, like the one at the center of our galaxy, where unimaginable gravitational forces might act as natural particle slingshots. Others proposed more exotic origins, defects in the fabric of space-time, or decaying dark matter particles from the early universe. But here's the kicker: the "oh my god" particles seem to come from empty space, a region with no known galaxies or energy sources. And then there's the travel problem. Particles this energetic should lose momentum as they collide with the cosmic microwave background, the faint glow left over from the Big Bang. By all rights, the "oh my god" particle should have fizzled out long before reaching Earth. Yet here it was, defying every expectation. Was it a freak accident or evidence of physics we don't yet understand? Decades later, we still don't have answers, just more questions. What if this particle is a glimpse into a hidden layer of the universe, one where the rules we know don't apply? The "oh my god" particle didn't just break records, it shattered assumptions. For decades, physicists had relied on something called the Greisen-Zatzepin Kuzmin limit, or GZK for short, to explain why we shouldn't see cosmic rays at such extreme energies. The theory was simple. Particles traveling across the universe should lose energy as they collide with photons from the cosmic microwave background, the faint echo of the Big Bang. By the time they reach us, their energy should drop below a certain threshold. but the oh my god particle laughed at that limit. It arrived with energy so high, it shouldn't have been possible under the rules we thought governed the cosmos. This left scientists with two unsettling possibilities. Either the particle came from somewhere much, much closer than we realized, maybe even within our own galaxy, or our understanding of particle physics is missing a critical piece. The first option is tricky because no known source in our cosmic neighborhood can produce such energies. The second, well, that opens the door to entirely new physics. Some theorists speculate these particles might be interacting with hidden dimensions or exotic matter we haven't discovered yet. Others wonder if they're the fingerprints of cosmic strings, hypothetical defects in spacetime left over from the universe's birth. To solve the mystery, researchers have built an arsenal of detectors. The Pierre Auger Observatory in Argentina, a sprawling array of water tanks and telescopes, scans the skies for ultra-high-energy cosmic rays. Over in Tibet, the AS-Gamma experiment hunts for gamma rays that might hint at these particles' origins. And then there's the telescope array in Utah, where the oh my god particle was first spotted, still waiting for another record breaker. But here's the frustrating part. Despite decades of searching, we've barely scratched the surface. These particles are so rare, catching one is like waiting for a single raindrop to hit a coin from miles away. Every detection is a clue, but the puzzle remains unsolved. What's clear is that the oh my god particle wasn't just a fluke, it was a wake-up call. The universe has energy factories we don't yet understand, and whatever they are, they're operating beyond the limits of our current science. So while we wait for the next cosmic bolt from the blue, one thing's certain: the answers, when they come, won't just rewrite a chapter in a textbook. They might rewrite the entire book, and that's what makes this hunt so electrifying, because out there, in the vast darkness, something is firing bullets we can't yet explain. If the oh my god particle represents the universe's most extreme cosmic rays, then what happens when we look at the other end of the energy scale? Around 1 peta-electron volt, that's 1,000,000 times less energy, but still a staggering amount. Something strange occurs. Scientists call it the knee of the cosmic ray spectrum, a point where the number of particles suddenly drops off like a hiker stumbling off a cliff. It's as if the universe has an invisible speed limit, a boundary where the rules change without warning. So what's causing this abrupt dip? One leading theory points to our own Milky Way. Imagine cosmic rays as tiny pinballs zipping through the galaxy's magnetic fields. Up to a certain energy, these fields can trap particles, keeping them bouncing around like pinballs inside a machine. But once particles reach the knee's energy threshold, around 1 peta-electron volt, they suddenly become too fast, too powerful to be contained. They punch through the galactic magnetic barriers and escape into intergalactic space, leaving behind the noticeable drop in numbers we detect. Then there's the supernova connection. For decades, scientists suspected that the shock waves from exploding stars could act as natural particle accelerators, boosting cosmic rays to these energies. The math seemed to fit until we realized supernovas might not be powerful enough to push particles past the knee. Some researchers suggest wildly energetic pulsars or even merging neutron stars could be the real culprits, injecting extra energy into the mix. Others speculate that something far stranger might be happening, perhaps a shift in how particles interact with the turbulent magnetic soup of our galaxy. But here's the twist: the knee isn't sharp, it's more of a bend, a gradual decline that varies slightly depending on where and how we look. Some detectors see a steeper drop, others a subtler curve. This inconsistency has fueled debates over whether we're seeing one unified phenomenon or multiple overlapping effects. Could there be different populations of cosmic rays, some from supernovas, others from hidden sources, each with their own energy cutoffs? The mystery deepens when we compare the knee to another cosmic ray oddity, the ankle, a much higher energy point where the particle count unexpectedly rises again. Together, these features hint at a complex cosmic ecosystem with different mechanisms governing low-energy and high-energy particles. Some theorists argue the knee marks the end of galactic cosmic rays, while the ankle signals the rise of extragalactic ones. If true, the knee isn't just a curiosity, it's a cosmic border, a dividing line between the particles born in our galaxy and those that journeyed across the void. Yet despite decades of study, no single theory fully explains the knee. It's a problem that's both tantalizing and frustrating, a reminder that even in our own galactic backyard, the universe keeps its secrets close. New detectors like the Cherenkov Telescope Array and upgraded facilities at the Pierre Auger Observatory are hunting for clues, hoping to catch enough particles near this critical energy to spot patterns or anomalies. What makes the knee so fascinating isn't just the science, it's the philosophy. This unassuming bend in a graph forces us to ask, are we missing a fundamental piece of how the cosmos works? Or is the knee simply a signpost pointing toward deeper mysteries we've yet to uncover? Either way, one thing's clear. In the hunt for answers, every new detection brings us closer to rewriting the story of our universe's hidden engines. Deep in the heart of the International Space Station, a machine called the Alpha Magnetic Spectrometer, or a MS-02, has been quietly collecting clues to one of cosmic rays' strangest riddles, an unexpected flood of positrons bombarding Earth from deep space. Positrons, the antimatter twins of electrons, should be rare. When matter and antimatter meet, they annihilate in bursts of energy, leaving behind very little. Yet a MS-02, along with earlier experiments like PAMEL and Fermi, detected something startling. At energies above 10 giga-electron volts, positrons aren't just present, they're overwhelming. They outnumber predictions by as much as 3-to-1, forming a mysterious excess that climbs steadily with energy before abruptly dropping off. So what's showering us with these antimatter particles? One leading suspect lurks in our own galactic backyard, pulsars. These rapidly spinning neutron stars act like cosmic lighthouses, shooting out beams of radiation and particles. As their powerful magnetic fields whip charged particles to extreme speeds, they could be churning out electron-positron pairs in vast quantities. The nearby Geminga pulsar, just 800 light-years away, is a prime candidate. Its turbulent surroundings seem to crackle with the right kind of energy. But here's the catch: while some pulsars fit the data, others don't. The positron excess is smoother and more uniform than pulsar models predict, as if something else or someone else is tuning the signal. Then there's the dark matter angle. If dark matter consists of weakly interacting massive particles, or WIMPs, colliding pairs of these invisible particles could annihilate and produce positrons as a byproduct. It's an elegant solution, tying one cosmic mystery to another, except the energy spectrum doesn't quite match. Most dark matter models predict a sharp drop in positrons at high energies, but the data shows a gradual decline. Some theorists tweak the models, suggesting heavier or more complex dark matter particles, while others argue we might be seeing multiple sources overlapping, like pulsars and dark matter both contributing. The plot thickens when we consider alternative astrophysical engines. Could microquasars, small-scale versions of the supermassive black holes that power quasars, be pumping out positrons as they devour nearby matter? Or what about remnants of ancient supernova, where shockwaves might still accelerate particles to extreme energies? Even ordinary cosmic rays slamming into interstellar gas could produce positrons, though calculations suggest they'd fall short of explaining the excess. But the most tantalizing possibility, that we're seeing the fingerprints of something entirely new. Some researchers speculate about exotic objects like primordial black holes or decaying cosmic strings, relics from the universe's earliest moments that might leak antimatter as they evaporate or vibrate. Others wonder if the excess hints at flaws in our understanding of particle physics itself, like hidden dimensions or unknown forces tweaking how particles behave at high energies. For now, the debate rages on. New data from upgraded detectors and future missions like the proposed All-Sky Medium Energy Gamma Ray Observatory, or MEGO, could tilt the scales toward one explanation or upend them all. What makes the positron excess so thrilling isn't just the mystery itself, but what it represents, a crack in the doorway of our understanding, where the faintest glimmer of something extraordinary might be shining through. Until we know for sure, every positron counted is a breadcrumb on the path to answers and possibly to rewriting the rules of the cosmos. If the knee of the cosmic ray spectrum is a puzzling dip, then the ankle is its enigmatic counterpart, an unexpected upturn that defies simple explanation. Around 1 exa-electron volt, or 1 billion times the energy of a proton in the Large Hadron Collider, the cosmic ray count suddenly stops dropping and starts to flatten. It's as if the universe hit a cosmic reset button, shifting gears from scarcity back to abundance. But why? What's happening at this critical energy threshold that makes particles reappear in greater numbers? The leading theory suggests we're witnessing a cosmic handoff, the moment where galactic cosmic rays born within the Milky Way give way to their extragalactic cousins. Imagine our galaxy as a bustling factory producing particles up to a certain energy, while beyond its borders, even more powerful accelerators take over. Supermassive black holes at the centers of distant galaxies, devouring matter and spewing jets of plasma, could be catapulting particles to these extreme energies. Colliding galaxy clusters with their chaotic magnetic fields might act as natural particle colliders on an unimaginable scale. Even active galactic nuclei, blazing with radiation, could be firing cosmic rays across the void like interstellar artillery. But there's a problem. If extragalactic sources dominate above the ankle, their particles should arrive uniformly from all directions, their paths scrambled by the tangled magnetic fields between galaxies. Yet some ultra-high-energy cosmic rays seem to cluster in suspiciously tight groups, as if pointing back to specific hotspots. The Telescope Array project in Utah, for instance, detected a so-called hotspot in the northern sky, a region spewing an unusual number of high-energy particles. If these rays are truly extragalactic, why aren't their origins more randomized? Alternative explanations twist the plot further. Some theorists propose that the ankle marks not a shift in source, but a change in how particles lose energy as they travel. Above this threshold, protons might interact differently with the cosmic microwave background, losing less energy over vast distances and thus appearing more abundant. Others speculate about exotic physics, perhaps a new type of particle, or even relics from the early universe, masquerading as ordinary cosmic rays. Could decaying super-heavy dark matter, left over from the Big Bang, be injecting fresh particles at these energies? Then there's the production puzzle. Even if extragalactic sources exist, how do they pump particles up to such monstrous energies? The most powerful events we know of, quasar jets, gamma-ray bursts, still struggle to explain the extremes we observe. Some models invoke shock waves from galaxy mergers or turbulent plasma bubbles, while others flirt with more speculative ideas like cosmic strings or primordial black holes evaporating in bursts of radiation. The ankle isn't just a curiosity, it's a boundary, a line in the sand separating two regimes of cosmic ray production. Solving its mystery could reveal whether we're seeing the limits of known astrophysics or the first hints of something entirely new. With next-generation detectors like the Giant Radio Array for neutrino detection and the upgraded Pierre Auger Observatory coming online, we might finally get the data to crack this cosmic code. Until then, the ankle remains a tantalizing clue in the universe's greatest energy mystery, one that refuses to fit neatly into any textbook. On June 30, 1908, a blinding flash lit up the skies over Siberia. Minutes later, a shockwave flattened 800 square miles of forest trees blown outward like matchsticks, their trunks seared and stripped bare. The Tunguska event remains one of history's most cataclysmic cosmic mysteries, and for decades, scientists assumed they knew the culprit, a stony meteoroid exploding in Earth's atmosphere. But what if the truth is stranger? What if the devastation wasn't caused by a rock from space, but by something far more exotic? Enter the cosmic ray hypothesis. Some researchers argue that Tunguska's peculiar details, the absence of a crater, the bizarre radiant burn patterns, the eerie lack of meteoric debris point to an ultra-high-energy cosmic ray slamming into our atmosphere. Here's how it might work. A single particle, accelerated to unimaginable speeds by some distant cosmic accelerator, could have struck the upper atmosphere with the force of a nuclear bomb. As it collided with air molecules, it would trigger a cascading shockwave of secondary particles, unleashing a fireball and blast wave without leaving behind any physical fragments. Then there's the antimatter twist. Another fringe theory suggests Tunguska was the annihilation of a chunk of antimatter, perhaps a meteor-sized piece of anti-iron meeting ordinary matter in a flash of pure energy. No debris, no crater, just an instantaneous conversion of mass into a titanic explosion. It's a tantalizing idea, especially since antimatter reactions release energy 1,000 times more efficiently than chemical explosives. But there's a catch. Where would such a large chunk of antimatter come from? Natural antimatter in space is vanishingly rare, and no known cosmic process could assemble it into concentrated, stable clumps. Mainstream science, of course, favors the airburst theory. Computer models show a 60-meter-wide stony asteroid entering at 15 kilometers per second could disintegrate 5 to 10 kilometers up, releasing energy equivalent to 10 to 15 megatons of TNT, enough to match Tunguska's devastation. In 2013, mineral fragments recovered from nearby peat bogs were tentatively linked to a meteoritic origin, yet even this explanation leaves gaps. Why did witnesses report strange luminous clouds lingering for days? Why did some trees at ground zero remain standing, their branches scorched off but trunks oddly intact? The debate rages because Tunguska sits at the edge of our understanding. Cosmic rays and antimatter are wild cards, rare, poorly understood, and capable of defying expectations. If either played a role, it would rewrite the rules of planetary impacts. Until we find definitive proof, Tunguska remains a haunting reminder. Sometimes the universe's most violent acts leave behind only questions. And that's what makes this mystery endure, not just the scale of the destruction, but the unsettling possibility that we might not yet know what's truly capable of falling from the sky. Ultra-high-energy cosmic rays don't play by the rules we expect. When particles smash into Earth's atmosphere with energies exceeding 1 exa-electron volt, each carrying the punch of a tennis ball served at 100 miles per hour, you'd think they'd point straight back to their birthplaces. But here's the twist: they don't. Instead of arriving in neat, traceable paths from distant galaxies or violent cosmic events, these particles scatter across the sky in what scientists call an isotropic distribution. It's as if someone took a handful of cosmic sand and tossed it uniformly in every direction, erasing all clues to its origin. So why doesn't the universe leave breadcrumbs? The answer lies in the invisible maze of magnetic fields crisscrossing space. Imagine a cosmic ray as a bullet fired through a hall of mirrors. Even if it starts its journey from a single, identifiable source, the tangled magnetic fields between galaxies act like those mirrors, bending and twisting its path until its original trajectory becomes hopelessly scrambled. By the time it reaches us, its arrival direction tells us almost nothing about where it began. These deflections aren't minor course corrections. They can send particles veering by tens of degrees over vast distances, turning pinpoint origins into a blur of possibilities. But the plot thickens. Some ultra-high-energy cosmic rays do seem to cluster in suspiciously tight groups, hinting at hidden hotspots in the cosmos. The Pierre Auger Observatory, a sprawling array of detectors in Argentina, has spotted faint but tantalizing patterns in the data regions of the sky where these particles appear more frequently than chance alone would allow. One such hotspot lies in the direction of Centaurus A, a nearby active galaxy with a supermassive black hole at its core. Could this be a cosmic fingerprint or just a statistical fluke? The debate rages because magnetic scrambling makes certainty impossible. Even if a ray seems to point toward Centaurus A, it might have originated somewhere entirely different, its path warped by magnetic detours we can't fully map. Then there's the energy problem. The highest energy cosmic rays should, in theory, be the easiest to trace. Their tremendous momentum ought to make them less susceptible to magnetic deflection, like a speeding freight train resisting a gentle breeze. Yet they still arrive isotropically, defying expectations. Some researchers speculate this could mean their sources are distributed evenly across the universe. No single galaxy or event stands out because the engines producing these particles are everywhere. Others wonder if we're missing a key piece of physics, like unknown magnetic structures or even exotic particles that interact differently with interstellar fields. The challenge isn't just scientific, it's technological. To untangle this mess, we need detectors with unprecedented precision. Projects like the proposed probe of extreme multi-messenger astrophysics aim to catch these rays in tandem with neutrinos or gamma rays, hoping multiple messengers will help triangulate their origins. Meanwhile, advanced simulations try to model the galactic and extragalactic magnetic fields that twist particle paths, turning cosmic noise into a decipherable map. What makes this mystery so compelling isn't just the puzzle itself, it's what it reveals about our place in the cosmos. We're surrounded by invisible highways of energy, particles flung across the universe by forces we can barely imagine. And every time one of these ultra-high-energy cosmic rays streaks through the atmosphere, it carries a story we're still learning to read. The universe isn't just hiding its secrets, it's encoding them in a language of deflections and detours, daring us to look deeper. In the high-altitude plains of Bolivia, cosmic ray detectors once picked up something that shouldn't exist, a particle shower so bizarre, scientists nicknamed it the Centauro event. Unlike typical cosmic ray collisions, which produce predictable sprays of particles, these events seem to spit out an overwhelming number of hadrons, protons, and neutrons, while curiously lacking the pions and other particles you'd normally expect. It was as if the universe had rewritten the rulebook for high-energy physics, leaving researchers scratching their heads. The strangeness doesn't stop there. Centauro events tend to be incredibly lopsided, with most of the particles blasting out in one direction like a cosmic shotgun blast. Ordinary air showers spread particles evenly, like a firework exploding in all directions. But they're more like a bullet shattering on impact, leaving behind a trail of debris that defies every model we have. So what's behind this anomaly? One radical theory points to strange quark matter, a hypothetical form of matter where quarks, the building blocks of protons and neutrons, aren't confined in threes but float freely in a bizarre quark soup. If chunks of this exotic material exist in space, they could be colliding with our atmosphere, releasing bursts of particles that behave nothing like ordinary matter. Imagine dropping a glass of water into a vat of acid. The reaction would be violent, unpredictable. That might be what's happening when strange quark matter meets Earth's atmosphere. Then there's the experimental wild card. Could these events just be glitches, misreadings caused by faulty detectors or atmospheric interference? It's possible, but the consistency of their peculiar signatures makes that hard to swallow. Multiple independent observations from the Chacaltaya Observatory in Bolivia to experiments in Japan have recorded similar patterns, ruling out simple equipment errors. The implications are staggering. If Centauro events are real, if they truly represent a new form of matter or an unknown physical process, they could reshape our understanding of particle physics. Some theorists even float the idea that these showers are evidence of microscopic black holes evaporating in our atmosphere, or relics from the early universe crashing into modern-day Earth. Yet for all the speculation, the truth remains elusive. No current particle accelerator can recreate the energies involved, leaving us to piece together clues from these rare, fleeting collisions. New projects like the Andes Large Area Particle Detector aim to catch more of these events, hoping to pin down their origins. Until then, Centauro showers stand as a haunting reminder. The universe is still capable of throwing curveballs we can't even begin to predict. Just 1,000 light-years from Earth, nestled in the constellation Gemini, a dead star spins at breakneck speed 30 times every second, hurling beams of radiation into the void. This is Geminga, one of the closest pulsars to our solar system, and for decades it hid a cosmic secret right under our noses. Astronomers first detected it in the 1970s as a faint, flickering gamma-ray source, its name literally meaning "it's not there" in the Milanese dialect, a playful nod to how long it eluded identification in visible light. But the real surprise came later, when researchers realized this unassuming pulsar might be peppering our neighborhood with something far more mysterious than gamma rays, cosmic rays. Here's what makes Geminga so perplexing. Pulsars are known for their lighthouse-like beams of electromagnetic radiation, but cosmic rays, those require a different kind of physics. When a pulsar's powerful magnetic field whips charged particles to nearly light speed, those particles can escape into space as cosmic rays. Geminga, with its intense magnetic environment and rapid spin, seemed like a perfect candidate except for one problem. Its gamma-ray signature was so bright, it drowned out any hints of cosmic rays in early observations. The smoking gun arrived when scientists noticed something odd about the space around Geminga. A vast, faint bubble of high-energy particles, stretching dozens of light-years across, seemed to glow in X-ray and gamma-ray observations. This wasn't just random noise, it was a cosmic ray halo, a telltale sign that particles had been leaking away from the pulsar for millennia. Like breadcrumbs left behind by an invisible traveler, these particles traced back to Geminga's violent past, but the plot twists deeper. If Geminga is such a prolific cosmic ray factory, why aren't we drowning in its particles? The answer lies in a cosmic game of hide and seek. Unlike gamma rays, which travel in straight lines, cosmic rays are charged, veering off course as they pass through interstellar magnetic fields. By the time Geminga's rays reach us, their paths are so scrambled they appear to come from all directions, masking their origin. It took sophisticated computer models to untangle the mess, revealing that this pulsar might be responsible for a significant fraction of the cosmic rays we detect near Earth. The implications are staggering. If Geminga, a relatively quiet, middle-aged pulsar, can churn out cosmic rays at this scale, what does that mean for the thousands of other pulsars scattered across the galaxy? Could these spinning stellar corpses be the hidden powerhouses behind the cosmic rays we've been detecting for over a century? Yet Geminga isn't giving up its secrets easily. Recent studies suggest its cosmic rays might have an unexpected energy profile, challenging existing models of how pulsars accelerate particles. Some theorists argue that turbulence in the pulsar's surroundings could be supercharging particles beyond what standard theories predict. Others wonder if Geminga's unique history, a supernova explosion that left it racing through space at hundreds of kilometers per second, plays a role, its motion stirring up particle acceleration in ways we don't yet understand. What's clear is that Geminga forces us to rethink the cosmos's quiet corners. Sometimes the most profound mysteries aren't in the distant, dazzling explosions, but in the faint, persistent glow of a nearby relic, one that's been whispering its story to us all along, if only we'd known how to listen. In the vast, seemingly random sea of cosmic rays raining down on Earth, astronomers occasionally stumble upon something startling: concentrated patches of the sky where these particles arrive in unexpected numbers. One of the most intriguing sits near the constellation Ursa Major, where detectors have recorded a curious overabundance of ultra-high-energy cosmic rays. Dubbed the hotspot, this region defies the usual isotropic distribution, sparking fierce debates. Is this a statistical mirage, or could it be the first faint trace of a hidden cosmic accelerator lurking in our galactic backyard? At first glance, the hotspot seems too good to be true. Cosmic rays are notoriously slippery to trace, their paths twisted by magnetic fields into near randomness. Yet here's a patch of sky, roughly 40 degrees across, where the Pierre Auger Observatory in Argentina and later the telescope array in Utah detected 20% more ultra-high-energy particles than background noise should allow. The odds of this happening by chance, less than 1 in 10,000. That's the kind of anomaly that makes physicists sit up and take notice. So what could be lurking in that direction? One compelling candidate is Centaurus A, the closest active galaxy to Earth, bristling with a supermassive black hole that spews jets of plasma into intergalactic space. If any structure could slingshot particles to such extreme energies, it's the chaotic maelstrom surrounding an active galactic nucleus. But there's a hitch. Centaurus lies slightly askew from the hotspot center, and current models struggle to explain how its rays could spread so widely without losing coherence. Other suspects include galaxy clusters like Virgo or M87, their turbulent magnetic fields possibly funneling particles toward us in a focused beam. Then there's the alternative camp skeptics who argue the hotspot might be a cosmic illusion. Magnetic fields between galaxies are poorly mapped, and even slight errors in modeling their deflections could make random clustering appear significant. Simulations show that under certain conditions, what looks like a hotspot could just be a chance alignment of particles scattered by invisible magnetic whirlpools. It's like seeing faces in clouds. The human brain is wired to find patterns even where none exist. The debate gets even murkier when we consider time. Cosmic ray hotspots aren't static. Some studies suggest the Ursa Major anomaly might flicker over decades, as if the source itself waxes and wanes in activity. Could this be a sign of intermittent cosmic engines, black holes with variable outbursts, or pulsars that occasionally rev up their particle acceleration? Or is it just the statistical noise of rare, high-energy events piling up in our detectors? New observatories aim to settle the argument. The upgraded Pierre Auger array, with its enhanced sensitivity, is scanning the hotspot for finer details, while plans for the next-generation giant radio array for neutrino detection promise to cross-check cosmic rays with neutrino arrivals, adding a second messenger to the hunt. If neutrinos, uncharged and unaffected by magnetic fields, cluster in the same direction, it would be smoking gun evidence of a true source. What's at stake isn't just the origin of one odd patch of sky. If the hotspot is real, it could crack open the century-old puzzle of where cosmic rays come from. If it's a fluke, it forces us to confront just how much we still don't understand about the invisible forces shaping particle journeys across the cosmos. Either way, the answer lies in that faint, tantalizing excess, a cosmic whisper waiting to be decoded. Deep in the void between stars, the alpha magnetic spectrometer aboard the International Space Station detected something that shouldn't exist: antihelium nuclei drifting through space. These aren't just any particles, they're the antimatter counterparts of helium atoms forged in conditions so extreme, they defy our understanding of cosmic chemistry. When MS-02 spotted these fleeting signatures, it sent shockwaves through the physics community, because finding antihelium in the wild is like discovering a snowball in a volcano. It simply shouldn't survive long enough to reach us. So where could these anti-atoms come from? One electrifying possibility: dark matter annihilations. If the invisible stuff making up 85% of the universe's mass consists of weakly interacting massive particles, their collisions could produce sprays of antiprotons and antineutrons. Under just the right conditions, these antimatter building blocks might fuse into antihelium nuclei, a process as rare as it is spectacular. The math is tantalizing. Simulations show that certain high-energy dark matter interactions could generate antihelium at levels tantalizingly close to what MS-02 observed. It's a long shot, but if proven, it would be the first indirect evidence of dark matter's true nature. Then there's the cosmic archaeology angle. Some theorists suggest these particles might be fossils from the universe's birth, when matter and antimatter nearly annihilated each other in the Big Bang's aftermath. Tiny pockets of primordial antimatter could have survived, drifting for billions of years until colliding with normal matter and releasing antihelium as cosmic shrapnel. This would explain why the detected nuclei appear too energetic for conventional astrophysical processes like finding a perfectly preserved dinosaur bone in your backyard. But before we rewrite the textbooks, skepticism remains. The signal is faint, buried under noise from cosmic ray collisions. Alternative explanations abound. Perhaps high-energy protons smashing into interstellar dust create antihelium as a byproduct, or maybe our models of nuclear interactions in extreme environments need updating. Even the IMS team cautions that these detections could be statistical flukes, ghosts in the data that vanish with more observation time. The stakes couldn't be higher. Confirming extraterrestrial antihelium would open a new window into the universe's most elusive secrets. Future experiments like the General Antiparticle Spectrometer aim to catch these particles with higher precision, while labs at CERN are attempting to recreate antihelium in accelerators, studying how easily it forms in simulated cosmic conditions. What makes this mystery so gripping isn't just the science, it's the philosophical weight. If dark matter or primordial antimatter really is spraying these particles across the galaxy, we're not just observers of the cosmos anymore. We're detectives piecing together clues from particles that have journeyed across space and time to whisper their origins. And that's the beauty of cosmic rays. They're not just radiation. They're messages waiting to be decoded. Think of the moon as a cosmic detective's tool, not just reflecting sunlight, but casting an invisible shadow made of particles we can't see. Normally, when the moon passes between Earth and the sun, it blocks sunlight, creating a solar eclipse, but something eerier happens with cosmic rays. Detectors on Earth should see a shadow too, a dip in particle counts where the moon blocks incoming rays. Instead, they've found something baffling. The shadow isn't as dark as it should be, as if some cosmic rays are slipping around the edges, bending like light through a prism. This oddity isn't just a curiosity, it's a clue. The moon's shadow in cosmic ray data is a critical calibration tool, helping scientists check their detector's precision. If the shadow appears sharp and deep, it means the detector is accurately mapping particle directions. But when it's faint or smeared, something's interfering. That something turns out to be the tangled web of magnetic fields woven through our solar system. As cosmic rays, charged protons, and atomic nuclei race toward Earth, these fields nudge their paths, warping the moon's shadow into a fuzzy blotch. The amount of distortion reveals hidden details about the strength and structure of interplanetary magnetism, a force usually too faint to measure directly. Then there's the deficit mystery. Even accounting for magnetic bending, some detectors report fewer particles in the moon's shadow than predicted. One theory blames the solar wind, the stream of charged particles boiling off the sun. Like a gust scattering dust, it could push cosmic rays off course, widening the shadow beyond expected limits. Others speculate about more exotic physics. Perhaps particles interact with lunar soil in unexpected ways, or maybe magnetic fields near the moon itself create invisible barriers. The most tantalizing possibility, that we're glimpsing subtle flaws in our models of how charged particles behave at extreme energies. hinting at gaps in quantum electrodynamics itself. What makes this lunar shadow puzzle so valuable is its simplicity. Unlike distant galaxies or hypothetical dark matter, the moon is right here, a lab bench in the sky where we can test fundamental physics. Every time it passes overhead, it offers a new chance to measure, tweak theories, and ask, are we missing something? The answers might rewrite not just our maps of cosmic rays, but our understanding of the invisible forces shaping their journey. The sun doesn't just light up our days, it also shapes an invisible battle raging above our heads, one where solar storms clash with cosmic rays in a high-energy tug-of-war. Every 11 years, as the sun reaches the peak of its activity cycle, its magnetic field becomes a chaotic frenzy of sunspots and solar flares. These eruptions don't just create dazzling auroras, they unleash a torrent of charged particles that sweep through the solar system like a cosmic broom, scrubbing away incoming cosmic rays. Scientists call this the cosmic ray weather effect, and its impact is far more profound than you might think. Take the Fawbush decrease, a sudden drop in cosmic ray intensity that can happen within hours of a major solar storm. Named after the physicist who first documented it in 1937, this phenomenon occurs when a coronal mass ejection, a billion-ton cloud of magnetized plasma, slams into Earth's magnetic field, creating a temporary shield against deep space particles. Picture a surfer riding a wave. As the solar storm passes, it pushes cosmic rays aside, causing their numbers to plummet by as much as 20%. But here's the twist. Once the storm passes, cosmic ray levels don't just snap back to normal. They rebound slowly, sometimes taking weeks to recover, as if the solar system itself needs time to reset. This cosmic tug-of-war isn't just academic. It has real-world consequences for technology and even our climate. During periods of high solar activity, the drop in cosmic ray flux correlates with fewer disruptions to satellite electronics and power grids. Cosmic rays, when they strike Earth's atmosphere, create showers of secondary particles that can interfere with sensitive equipment. A strong solar storm might knock out GPS signals or overload transformers, but it also buys us a temporary reprieve from these invisible space bullets. Then there's the climate connection. Some researchers propose that cosmic rays influence cloud formation by ionizing molecules in the atmosphere, acting as seeds for water droplets. If that's true, a Fawbush decrease could theoretically lead to fewer clouds and potentially warmer temperatures on short timescales. It's a controversial idea, but studies have spotted subtle correlations between cosmic ray dips and shifts in Earth's cloud cover. Whether this is a minor side effect or a major climate driver remains hotly debated, but it underscores how intricately linked we are to the cosmos's ebb and flow. What makes cosmic ray weather so fascinating isn't just the science, it's the scale. A storm on the sun can ripple across 93 million miles of space, reshaping the particle environment around our planet in ways we're only beginning to understand. And with every solar cycle, we get a front-row seat to this cosmic drama, where the sun's fury and the galaxy's invisible rays vie for dominance over our tiny corner of space. In 2008, a satellite named PAMEL, short for Payload for Antimatter Matter Exploration and Light Nuclei Astrophysics, detected something that sent shockwaves through particle physics. Orbiting 350 kilometers above Earth, its sensitive instruments picked up an unexpected flood of positrons, the antimatter counterparts to electrons streaming through space. At energies above 10 giga-electron-volts, these positrons weren't just present. They were overwhelming, outnumbering theoretical predictions by a factor of 3. It was as if the universe had flipped a hidden switch, flooding our cosmic neighborhood with particles that should have been vanishingly rare. What made this discovery so explosive wasn't just the excess itself, it was how cleanly it contradicted decades of assumptions. Conventional models had long suggested that most positrons in cosmic rays should come from secondary processes, like protons colliding with interstellar gas. These collisions produce electron-positron pairs, but the numbers should taper off at higher energies. PAMELA's data did the opposite. The positron fraction, the ratio of positrons to electrons plus positrons, rose steadily with energy, peaking around 100 giga-electron volts before mysteriously dropping off. It was a curve that screamed anomaly, a cosmic clue that something or someone was tipping the scales. The hunt for explanations was on, one leading suspect. Pulsars, those rapidly spinning neutron stars that act like cosmic lighthouses. As their powerful magnetic fields whip particles to near light speeds, they could be churning out electron-positron pairs in vast quantities. The Geminga pulsar, just 800 light-years away, quickly became a prime suspect. Observations showed it surrounded by a faint, glowing bubble of high-energy particles, evidence of positrons leaking into space. But skeptics pointed out a problem. PAMELA's positron excess was too smooth, too uniform, to match the lumpy distribution expected from nearby pulsars. It was like finding a perfectly mixed smoothie when you'd expected chunky salsa. Then came the dark matter enthusiasts. If dark matter consists of weakly interacting massive particles, or WIMPs, colliding pairs of these invisible particles could annihilate into positrons as a byproduct. The idea was elegant, tying one cosmic mystery to another, but the energy spectrum didn't quite fit. Most WIMP models predicted a sharp cutoff in positrons at high energies, yet PAMELA's drop-off was more gradual, as if multiple sources were overlapping. Some theorists tweaked their equations, proposing heavier or more complex dark matter particles. Others wondered if both pulsars and dark matter were contributing, their signals blending into a single, confusing excess. Enter the follow-up experiments. In 2013, the Alpha Magnetic Spectrometer on the International Space Station confirmed PAMELA's findings with even higher precision, extending the measurements to energies of a tera-electron volt. A MS-02's data revealed something new. The positron fraction didn't just peak and fall, it plateaued, as if hitting a cosmic ceiling. Then, in 2017, the DAMP satellite, a Chinese mission, added another twist. At energies above 1 tera-electron volt, the positron fraction began dropping again, but not as steeply as some models predicted. Each new dataset was like adding another piece to a jigsaw puzzle, except the picture kept changing. Today, the PAMELA positron excess remains one of cosmic ray physics' most tantalizing unsolved cases. It's reshaped how we search for dark matter, forcing scientists to consider more exotic particle candidates and complex astrophysical backgrounds. It's also highlighted the limits of our instruments. No single experiment can yet pin down the excess's true origin. Future missions, like the proposed all-sky medium-energy gamma-ray observatory, aim to untangle this web by hunting for complementary gamma-ray signals that could pinpoint pulsars or dark matter annihilations. But perhaps the most profound legacy of PAMELA's discovery is what it taught us about cosmic humility. Sometimes the universe doesn't just hide its secrets, it wraps them in layers of ambiguity, forcing us to question not just what we see, but how we see it. The positron excess isn't just a puzzle to solve. It's a reminder that out there, in the vast dark, the rules we take for granted might be waiting to be rewritten. The universe has a built-in speed bump for cosmic rays, a point where even the most energetic particles should slam on the brakes. That's what physicists thought anyway, until they ran headfirst into the GZK paradox. Named after Grison, Zatsepin, and Kuzmin, who predicted it in 1966, the GZK limit is supposed to be the ultimate cosmic roadblock. Here's how it works. When ultra-high-energy cosmic rays streak across the universe, they inevitably collide with photons from the cosmic microwave background, the faint afterglow of the Big Bang. Each collision saps their energy like a marathon runner hitting endless walls of molasses. By the time these particles reach us, their energy should drop below 100 exa-electron volts. Anything above that, impossible, or so we thought. Yet over the years, detectors have caught multiple cosmic rays laughing in the face of this limit. The oh my god particle was just the beginning. Others, like the oh my god part 2 particle detected in 2021, have come screaming in with energies that, by all rights, should have been stripped away billions of years ago. It's like finding a perfectly preserved ice cube in the middle of a desert, a glaring violation of nature's rules. So how are these particles cheating the system? One theory suggests they're cosmic hitchhikers, born much closer to home than we assumed. If a supermassive black hole in our galactic neighborhood, like the one lurking at the center of the Milky Way, acted as a particle slingshot, it might fling rays to extreme energies without requiring them to cross vast intergalactic distances. But here's the snag: no known source in our corner of the universe packs enough punch to explain the most extreme detections. Another idea twists the fabric of reality itself. Maybe these particles aren't protons, the usual suspects, but heavier atomic nuclei. Iron nuclei, for example, could theoretically survive longer journeys because their larger size lets them plow through the microwave background with less energy loss. But even this falls short when faced with the highest energy events. Some theorists have gone further, proposing exotic physics like Lorentz invariance violation, a fancy way of saying the speed of light might not be the ultimate speed limit in all circumstances. If true, it would upend Einstein's relativity, rewriting the rules that govern the cosmos. The plot thickens when we consider alternative messengers. If ultra-high-energy cosmic rays interact with the microwave background, they should produce a shower of secondary particles, including neutrinos and gamma rays. Yet searchers for these byproducts, like the Ice Cube Neutrino Observatory's hunt for GZK neutrinos, keep coming up short. It's as if the universe is playing a shell game, hiding the evidence we need to crack the case. What makes the GZK mystery so gripping isn't just the defiance of a theoretical limit, it's what that defiance implies. Every particle that slips past this cosmic checkpoint forces us to question whether we've misunderstood the universe's architecture. Are we missing hidden particle accelerators lurking in the dark, or staring at the first cracks in our most cherished physical laws? Until we know one thing's certain, the cosmos isn't just testing its own rules. It's testing our courage to admit how much we still have left to learn. Buried beneath the plains of Argentina lies one of the most ambitious cosmic detective tools ever built, the Pierre Auger Observatory. Spanning an area larger than Rhode Island, its 1,600 water tanks and 24 fluorescence telescopes form a net designed to catch the rarest, most energetic particles in existence. For years, this mega experiment has been hunting a pattern in the chaos, trying to answer one question: do ultra-high-energy cosmic rays come from anywhere in particular? The answer, it turns out, is as tantalizing as it is frustrating. The data reveals hints of something called anisotropy, a fancy term meaning the particles aren't arriving uniformly from all directions. Instead, they cluster weakly but persistently around the positions of active galactic nuclei, the violent cores of distant galaxies powered by supermassive black holes. One particularly notable hotspot aligns roughly with Centaurus A, the closest known active galaxy to Earth, just 13 million light-years away. It's a compelling lead, except nothing in cosmic ray astronomy is ever that simple. Active galactic nuclei make perfect suspects. They're black holes, some weighing billions of times the Sun's mass, launch jets of plasma at near light speed, creating natural particle accelerators of staggering power. But here's the catch: the correlation isn't definitive. The anisotropy signal detected by Auger sits at around 4 sigma, strong enough to raise eyebrows but not quite the gold standard 5 sigma needed for a conclusive discovery. It's like hearing a whisper in a crowded room. You're almost sure you caught a name, but you can't swear to it. Then there's the deflection problem. Ultra-high-energy cosmic rays are charged particles, meaning their paths twist and bend as they travel through the galaxies and intergalactic magnetic fields. Even if they originated from a single point, their arrival directions could be smeared across huge swaths of sky by the time they reach us. Some simulations suggest the observed anisotropy might actually be a cosmic mirage particles from completely different sources scattered into artificial clusters by these invisible magnetic lenses. The plot thickens when you compare Auger's findings with other experiments. The telescope array in Utah spotted its own hotspot, but it's not in the same part of the sky as Auger's. Is this evidence of multiple cosmic accelerators or just statistical noise? Without more data, the debate rages on. What makes this anisotropy hunt so electrifying isn't just the science, it's the stakes. If active galactic nuclei really are the engines behind these extreme particles, it would solve a century-old mystery. But proving it requires catching more of these elusive rays and mapping their paths with even greater precision. Upgrades to Auger and new observatories like the proposed Cosmic Ray Extremely Distributed Observatory aim to do just that, sharpening our cosmic vision. For now, the anisotropy remains a shadow on the data, a flicker of order in the chaos. It's a reminder that sometimes the universe doesn't just hide its secrets. It teases them, giving us just enough to keep us searching. Deep in the heart of our galaxy, an invisible storm rages, one we can only detect through the faintest glimmers of light. The Milky Way center should be a graveyard of gamma rays, the remnants of countless cosmic collisions. But when scientists pointed telescopes like Fermi toward this region, they saw something startling, a bizarre excess of gamma radiation, pulsing with energies that should be impossible if our current models are correct. Some believe this glow could be the ghostly fingerprint of dark matter particles we've never seen, annihilating each other in the dark and leaving behind bursts of energy as their only trace. The logic is simple. If dark matter consists of weakly interacting massive particles WIMP, then where they cluster most densely, like the galactic core, pairs of these particles should occasionally collide and annihilate. The byproducts, gamma rays, positrons, and other high-energy signatures we might spot in cosmic rays. The Fermi gamma ray excess fits part of this picture beautifully. Its energy spectrum matches roughly what some dark matter models predict, and its distribution aligns with where theorists think dark matter should be concentrated. It's like seeing smoke and wondering if there's an unseen fire. But here's the catch, not all smoke comes from fire. Alternative explanations abound. The excess could come from a dense population of pulsars spinning neutron stars too faint to detect individually, but collectively flooding the region with gamma rays. Or it might trace back to cosmic rays slamming into gas clouds, a process that also produces gamma radiation. Even rogue millisecond pulsars, ancient stellar remnants revved up to incredible speeds, have been proposed as culprits. The debate hinges on nuance. Dark matter annihilation should produce a smooth gamma ray glow, while pulsars would create a speckled pattern. Current data isn't sharp enough to settle the argument. It's like trying to count distant streetlights through thick fog. Then there's the AMS-02 puzzle. The Alpha Magnetic Spectrometer on the International Space Station has spent years counting cosmic ray positrons, and it's found an excess eerily similar to what some dark matter models predict. But again, pulsars muddy the waters. The nearby Geminga pulsar, for instance, could be pumping out positrons at just the right energies to mimic a dark matter signal. The real frustration, these two explanations aren't mutually exclusive. The excess could be a mix of both astrophysical sources and dark matter, leaving scientists to tease apart contributions like detectives separating overlapping fingerprints. What makes this hunt so electrifying isn't just the science, it's the stakes. If the gamma ray excess or the positron anomaly truly comes from dark matter, it would be one of the greatest discoveries in physics, unlocking the secrets of 85% of the universe's mass. But if it's just pulsars or cosmic rays, it's still a remarkable lesson in how complex the cosmos can be. Future telescopes, like the Cherenkov Telescope Array, aim to sharpen our view of the galactic center, while next-generation cosmic ray detectors will scan for subtler clues in particle spectra. Until then, the data remains a riddle, one that keeps us questioning, searching, and staring into the dark, wondering what invisible hands might be shaping the universe around us. What if the spark of life wasn't just a lucky chemical reaction, but a bombardment from space? Among the wilder frontiers of astrobiology, there's a provocative theory suggesting cosmic rays didn't just pepper Earth's surface over billions of years. They might have directly shaped life's evolution by scrambling the genetic code itself. Picture this: high-energy particles screaming through the atmosphere strike a primordial pond filled with early organic molecules. Each collision acts like a microscopic lightning bolt, breaking chemical bonds and rearranging molecular structures in ways heat or sunlight alone couldn't achieve. Over eons, these relentless particle strikes might have nudged simple compounds toward complexity, accelerating the leap from chemistry to biology. This so-called cosmic ray mutation hypothesis sits at the edge of scientific respectability, but it's not without intriguing circumstantial evidence. Studies show that certain cosmic ray impacts can indeed trigger mutations in DNA, both destructive and creative. In modern organisms, radiation damage is usually harmful, but in a prebiotic world without delicate cellular machinery to protect, that same chaos could have acted as a randomizer, shuffling molecular building blocks until, by sheer chance, self-replicating molecules emerge. Some experiments even suggest cosmic rays could have helped synthesize ribose, the sugar backbone of RNA, under conditions mimicking early Earth. Yet mainstream abiogenesis theories, the study of life's chemical origins, remain skeptical. The dominant view focuses on gentler, more predictable drivers: hydrothermal vents cycling minerals and gases, tidal pools concentrating organic soups, or ultraviolet light providing steady energy for reactions. These environments offer controlled conditions where complex molecules can accumulate and interact without being shredded by high-energy particles. Critics of the cosmic ray hypothesis point out that while mutations are crucial for evolution, life first needed stability, a reliable template to copy before randomness could refine it. But here's where the debate gets fascinating. Cosmic rays might not have been the sole architects of life, but they could have been clandestine collaborators. Imagine Earth's early millennia as a vast experiment, with cosmic rays as the unpredictable variable. While thermal vents or volcanic ponds provided safe havens for molecules to assemble, periodic particle strikes could have injected bursts of innovation, pushing stagnant systems toward breakthroughs. It's a middle ground, one where cosmic rays weren't the hero or the villain, but the wild card that kept the game moving. The cosmic ray mutation theory forces us to reconsider life's origins not as a sheltered miracle, but as a cosmic dance of energy and chance. Whether it's proven or not, it underscores a humbling truth: life on Earth didn't evolve in isolation. From the very beginning, the universe has been an active participant, shaping our story with invisible hands. For all our theories about where cosmic rays come from, there's an unsettling gap in the story: a cosmic whodunit with no clear culprit. We've spent decades pointing to supernova, pulsars, and active galactic nuclei as the likely particle accelerators behind these high-energy messengers. Yet when we tally up the numbers, something doesn't add up. The universe's most powerful cosmic rays arrive with energies so extreme, they defy even our most generous estimates of what these cosmic engines should produce. It's as if we've been searching for a flashlight in the dark, only to realize the light we're seeing is coming from a lighthouse no one's ever spotted. Take supernova, the explosions of dying stars long considered the primary cosmic ray factories. The math makes sense: at lower energies, shockwaves from these blasts can accelerate particles to impressive speeds. But when we look at the very highest energy cosmic rays, the numbers just don't line up. even the most violent supernova remnant falls orders of magnitude short of the punch needed to create particles like the oh my god event. It's like trying to power a rocket with a firecracker. The mechanism might be similar, but the scale is all wrong. Pulsars aren't off the hook either. These spinning neutron stars with their dizzying magnetic fields can certainly sling particles to incredible speeds. Geminga, for instance, shows us they're capable of churning out cosmic rays in surprising quantities. Yet when we calculate how much energy even the most extreme pulsar can inject into a single particle, we hit the same wall. The highest energy cosmic rays we detect carry kinetic energy comparable to a well-thrown baseball packed into a single proton. No known pulsar, no matter how fast it spins or how strong its magnetic field, can explain that kind of firepower. Then there's the case of active galactic nuclei, the supermassive black holes at the hearts of galaxies. These monsters, with their jets of plasma stretching thousands of light years, seem like perfect candidates. Surely nothing in the universe can accelerate particles more efficiently than a black hole's gravitational fury. But here's the catch. While active galaxies can theoretically produce ultra-high-energy cosmic rays, the ones we've identified are too far away. The microwave background radiation filling the universe should have sapped the energy from any particles traveling those vast distances. It'd be like a marathon runner sprinting non-stop for 100 miles. By the time they reach the finish line, they'd be crawling. Yet these cosmic rays arrive fresh as ever, their energy intact. This leaves us with three possibilities, each more tantalizing than the last. First, we're missing something fundamental about how known sources like supernova or black holes work. Maybe turbulence in their surroundings or hidden magnetic structures can boost particles beyond our current models. Second, there's a completely new class of cosmic accelerators out there, something we haven't imagined yet. Some theorists speculate about dark galaxies made mostly of invisible matter, their black holes churning unseen. Others wonder if colliding galaxy clusters with their tangled magnetic fields could act as universe-sized particle colliders. But the third possibility is the most thrilling and the most unsettling. What if these cosmic rays aren't coming from any conventional source at all? What if they're the debris of exotic physics, decaying dark matter, evaporating primordial black holes, or even defects in spacetime itself? The universe loves to surprise us, and every unexplained particle could be a clue to something deeper, something stranger. Until we find the smoking gun, one thing's certain: the case of the missing cosmic ray sources isn't just a gap in our knowledge. It's an open invitation to rethink everything we thought we knew about how the cosmos works. Could the fate of Earth's climate hinge on invisible particles from deep space? Among the most controversial ideas in atmospheric science is the notion that cosmic rays don't just streak harmlessly through our skies. They might actively shape our weather by seeding clouds. This theory, first proposed in the late 1990s, suggests that when high-energy particles collide with molecules in the atmosphere, they trigger chain reactions that form tiny aerosol clusters. These microscopic specks act as nucleation sites, inviting water vapor to condense around them until full-fledged clouds emerge. If true, it would mean the cosmos isn't just a backdrop to our climate, it's an active player, tweaking cloud cover and temperatures with every barrage of particles. The implications are staggering. During periods of high solar activity, the sun's magnetic field deflects more cosmic rays away from Earth, potentially reducing cloud formation and allowing more sunlight to reach the surface. Conversely, when solar activity wanes, like during the historic Maunder minimum in the 1600s, cosmic ray flux increases, possibly fueling denser cloud cover and global cooling. It's a tantalizing explanation for historical climate shifts that don't neatly align with greenhouse gas records. But here's where the debate ignites. Clouds are notoriously complex, influenced by everything from ocean currents to pollution. Teasing out a cosmic ray signal from this noise has proven brutally difficult. Enter CERN Cloud Experiment, a groundbreaking effort to simulate Earth's atmosphere in a controlled chamber. By bombarding artificial air mixtures with particle beams mimicking cosmic rays, scientists hope to catch the birth of cloud seeds in action. Early results sent shockwaves through the community. Under precise laboratory conditions, cosmic ray-like particles did indeed spur aerosol formation, especially when paired with trace gases like sulfuric acid or ammonia. But there's a catch. The aerosols created were often too small to efficiently grow into cloud-forming droplets without additional pollutants from human activity. In other words, cosmic rays might need a helping hand from industrial emissions to significantly impact clouds. Critics pounce on these nuances. They argue that while cosmic rays may play a minor role in ideal lab settings, real-world observations show little correlation between cosmic ray flux and major cloud changes. Satellite data from missions like Ceres reveals no clear global trend linking particle strikes to cloud cover variations. Even the famed Danish cloud physicist Henrik Svensmark, the theory's chief architect, concedes that cosmic rays are likely just one ingredient in a far more complex recipe. Yet the theory refuses to die. Recent studies have uncovered curious regional patterns. Over Antarctica, where the air is pristine and human pollution minimal, cosmic ray fluctuations show a stronger correlation with low-altitude cloud formation. Similarly, tree ring data spanning centuries hints at periods when cosmic ray spikes aligned with prolonged cooling, even when solar brightness remained stable. These pockets of evidence keep the debate alive, suggesting that while cosmic rays may not dominate global climate, they could nudge specific regions under the right conditions. What makes this mystery so gripping isn't just the science, it's the philosophical stakes. If cosmic rays influence clouds even slightly, it means Earth's climate is tethered to the galaxy in ways we're only beginning to map. A supernova explosion or passing interstellar gas cloud could, in theory, alter our planet's particle flux and weather patterns across millennia. It's a humbling reminder that we don't just live on a planet, we're embedded in a cosmic web of invisible forces, where the distant violence of stars might whisper into the wind and rain around us. Until we untangle these connections, every cloud in the sky remains a potential message, one written in particles from beyond our solar system. Hovering above and below the Milky Way's disk like two colossal hourglasses, the Fermi bubbles stretch 50,000 light-years into space, a pair of gamma-ray behemoths so vast they dwarf our entire galaxy. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these mysterious structures glow with energies that defy easy explanation. But hidden within their faint, diffuse light might lie clues to one of cosmic rays' most persistent riddles. Where do the highest energy particles get their unimaginable kick? The leading theory points to our galaxy's silent heart, a supermassive black hole named Sagittarius, a star. Though quiet now, astronomers suspect it wasn't always this docile. Millions of years ago, this gravitational monster might have erupted in a cataclysmic feeding frenzy, devouring vast clouds of gas and belching out jets of plasma at near light speed. These jets could have inflated the Fermi bubbles like cosmic balloons, while shockwaves rippling through them might have acted as natural particle accelerators, boosting cosmic rays to extraordinary energies. Imagine a tsunami crashing through the ocean, picking up debris and hurling it forward. That's how these shockwaves might sling protons and atomic nuclei across interstellar space. Yet not everyone's convinced. Alternative explanations paint a different picture. One camp argues the bubbles could be the aftermath of a starburst frenzy, a period when the galactic center spawned stars so rapidly, their combined supernova explosions pumped energy into the surrounding gas like a cosmic pressure cooker. Another faction points to dark matter, suggesting these faint gamma rays could be the glow of invisible particles colliding and annihilating in the galaxy's dark halo. Even the bubble's symmetrical shape raises questions. If they're truly ancient relics of a black hole outburst, why haven't galactic magnetic fields or stellar motions distorted them over millions of years? The cosmic ray connection adds another layer of intrigue. If the bubbles are indeed accelerators, they should produce a distinct fingerprint in the particles we detect on Earth, specific energy ranges or elemental mixes that differ from other sources. Some models predict an overabundance of heavy nuclei like iron, forged in the extreme environments near black holes. Others suggest these rays would arrive with telltale directional biases clustering around the galactic center. But so far, the data refuses to play along. Detectors like the Pierre Auger Observatory have found no conclusive link between ultra-high-energy cosmic rays and the bubble's location. What makes this puzzle so compelling isn't just the science, it's the scale. The Fermi bubbles are a fossil record of our galaxy's violent past, a reminder that even quiet spirals like the Milky Way have explosive secrets. Whether fueled by black holes, supernova, or something even stranger, their story is still being written, one gamma ray, one cosmic particle at a time. And every new observation brings us closer to understanding not just these colossal structures, but the invisible forces that shape the universe around us. For over a century, scientists tracking cosmic rays noticed something odd. Their numbers rise and fall in rhythmic patterns, as if the universe itself were breathing. One of the most persistent pulses is a 1.3-year cycle, a mysterious ebb and flow in cosmic ray intensity that defies simple explanation. Unlike the 11-year solar cycle, whose link to sunspot activity is well documented, this shorter oscillation has no obvious cosmic conductor waving the baton. The first clue lies in the solar wind, the stream of charged particles constantly gusting from the sun's upper atmosphere. Normally, this wind acts like a cosmic broom, sweeping lower energy rays away from the inner solar system. But the sun isn't a perfect metronome. Deep beneath its surface, overlapping layers of plasma churn at different speeds, creating hidden currents that may pulse the solar wind's intensity at irregular intervals. Some researchers speculate that the 1.3-year cycle could be the fingerprint of these subsurface dynamics, a hidden solar heartbeat tweaking the particle flux around Earth. Yet interstellar space whispers its own theories. Beyond the sun's influence, our solar system plows through a patchwork of gas clouds and magnetic fields, the local interstellar medium. As we move through this uneven terrain, the galactic environment's pressure might subtly modulate how easily cosmic rays penetrate the heliosphere, the protective magnetic bubble carved out by the solar wind. Imagine walking through a forest where tree density varies. Sometimes the canopy lets in more light, sometimes less. The 1.3-year cycle could reflect our passage through denser or sparser regions of this invisible galactic undergrowth. The plot thickens when we consider cosmological possibilities. Some models suggest that cosmic rays themselves might generate these fluctuations through feedback loops. High-energy particles colliding with interstellar gas could trigger secondary particle showers, whose remnants circle back to influence the primary cosmic ray flux. It's a cosmic echo chamber where the signal feeds itself, creating oscillations without any external trigger. Others wonder if the cycle is a statistical mirage, a clustering artifact emerging from the chaotic interplay of countless independent sources across the galaxy. What makes this puzzle so compelling isn't just the cycle itself, it's the discord between detectors. Instruments in the northern hemisphere sometimes pick up the 1.3-year signal more clearly than their southern counterparts, hinting at asymmetries in how cosmic rays arrive at Earth. Could our planet's own magnetic field or the solar wind's uneven structure be filtering these variations in ways we don't yet grasp? Every unanswered question underscores a humbling truth. Cosmic rays aren't just passive travelers from distant space. They're dynamic messengers, their fluctuations encoding secrets about everything from the sun's hidden depths to the galaxy's invisible topography. and until we crack their rhythmic code, we're left listening to a universe that keeps changing its tune. When a cosmic ray slams into Earth's atmosphere at nearly the speed of light, it doesn't arrive alone, it unleashes a cascade. Imagine a single, ultra-energized particle colliding with an air molecule, shattering into secondary particles, which then collide and shatter again, multiplying exponentially until millions of fragments rain down in what scientists call an extensive air shower. These particle avalanches span kilometers in width, detectable by ground-based observatories as fleeting bursts of light or radio waves. But here's where things get weird. Some showers don't play by the rules. Instead of the predictable mix of particles physics textbooks dictate, they arrive with bizarre imbalances: too many muons here, too few gamma rays there, as if the universe tossed a wrench into our best models of how matter behaves at extreme energies. Take muons, for instance. These heavy cousins of electrons should emerge from air showers in specific numbers, governed by the laws of hadronic interactions, the way particles like protons and pions collide and decay. Yet detectors routinely catch showers with muon counts 10 or even 20% higher than simulations predict. It's like baking a cake where the recipe calls for 2 eggs, but cracking open the oven to find a dozen. One possible explanation: our models of particle physics might be missing a hidden ingredient. Some theorists suggest that high-energy collisions in the upper atmosphere could briefly spawn exotic states of matter, like quark-gluon plasma, a primordial soup last seen microseconds after the Big Bang. These fleeting, ultra-dense blobs might decay differently than ordinary matter, skewing the particle ratios in ways we don't yet understand. Then there's the gamma-ray puzzle. In a typical shower, pions, short-lived particles produced in the initial collisions, should decay into gamma rays. But certain events, like those detected by the Cherenkov telescope array, show gamma-ray deficits so pronounced they've been dubbed gamma-poor showers. One radical theory blames hypothetical dark photons, particles that could siphon energy away from visible light into invisible channels. Another camp points to flaws in how we simulate atmospheric density fluctuations, arguing that tiny variations in air pressure might subtly reshape shower development. But neither explanation fully accounts for the scale of the anomalies. The most tantalizing clue lies in the shower's lateral spread. High-energy particles should fan out in predictable patterns like shrapnel from a grenade. Yet some events, like the famous fan shower caught by the Havre Park array in the 1970s, spray particles in lopsided jets as if something mid-collision deflected the cascade. Could unknown magnetic effects in the upper atmosphere be bending charged particles off course? Or are we seeing hints of new quantum behaviors where particles interact differently at energies too extreme to replicate in terrestrial labs? What makes these anomalies so maddening and so thrilling is their refusal to fit neatly into any single theory. Every unexplained shower is a crack in the facade of modern physics, a whisper that the rules we've written might only be half the story. Until we catch enough of these rogue cascades to spot a pattern, one thing's clear: the cosmos isn't just sending us particles. It's sending us riddles wrapped in showers of light and shadow, daring us to look deeper. Beneath the pristine ice sheets of Antarctica and locked within the rings of ancient trees lie hidden records of cosmic violence, a kind of interstellar archaeology written not in stone but in particles. Scientists have uncovered that cosmic rays leave behind faint but measurable imprints in Earth's natural archives, offering snapshots of our planet's bombardment by high-energy particles across millennia. The key to decoding this history: isotopes like beryllium-10 and carbon-14, rare forms of elements created when cosmic rays strike atoms in the upper atmosphere. These isotopes rain down, settling in ice and wood, where they accumulate in layers like pages in a cosmic diary. One of the most dramatic entries in this diary dates back to the year 774. Tree rings from that period contain a staggering spike in carbon-14, a surge so abrupt it points to an invisible deluge of cosmic rays striking Earth. The likely culprit, a nearby supernova unleashing a torrent of particles that briefly overwhelmed our planet's protective magnetic field. Historical records from the same era describe a red crucifix glowing in the night sky, possibly the fiery aftermath of a stellar explosion visible even in daylight. But here's the eerie part. No known supernova remnant from that time matches the expected location or brightness. Some theorists suggest it might have been a rare, failed supernova, where a massive star collapsed directly into a black hole without the usual fireworks, releasing a shockwave of particles instead of light. Ice cores add another layer to the mystery. In Greenland and Antarctica, researchers drilling deep into glaciers have found matching spikes in beryllium-10, an isotope produced when cosmic rays split nitrogen atoms in the atmosphere. These spikes don't just align with 774, they reveal earlier events like a dramatic surge around 541 AD, coinciding with a period of global cooling and crop failures. Could a hidden supernova or gamma-ray burst have triggered a mini-ice age? The data is tantalizing, though far from conclusive, but cosmic ray archaeology isn't just about ancient disasters. By studying these isotopic patterns, scientists are piecing together a timeline of the Sun's activity over centuries. During periods of high solar magnetism, like the medieval warm period, the Sun's enhanced magnetic shield deflects more cosmic rays, leaving fewer isotope traces in tree rings and ice. Conversely, the Little Ice Age, a stretch of bitter cold from the 14th to 19th centuries, aligns with a surge in cosmic ray flux, suggesting an eerily quiet sun. The challenge lies in separating cosmic signals from earthly noise. Volcanic eruptions, for instance, can also alter atmospheric chemistry, mimicking cosmic ray spikes. To weed out false positives, researchers cross-reference isotopes with other climate proxies like sulfur deposits or historical aurora records. It's a painstaking process, but the rewards are immense, a chance to read the universe's fingerprint in the very fabric of our planet. What makes this detective work so profound isn't just the science, it's the perspective. Every ancient tree, every layer of ice, holds echoes of stellar explosions we'll never see, of particles traveling light years to etch their mark on Earth. And as we decode these messages, we're not just studying the past. We're preparing for the next cosmic event, because somewhere out there, another star is winding up for a blast that might one day leave its own mark in the rings of an unborn oak. The future of cosmic ray science isn't just about building bigger detectors. It's about rewriting the rules of how we see the universe. Standing at the edge of discovery, next-generation observatories are gearing up to tackle mysteries that have baffled scientists for decades. Take the Cherenkov Telescope Array, or CTA, currently rising across 2 continents like a mechanical forest of light catchers. With over 100 telescopes split between Chile's Atacama Desert and Spain's Canary Islands, this network will scan the skies for gamma rays with 10 times the sensitivity of current instruments. But here's where it gets revolutionary. Instead of just spotting cosmic rays indirectly through atmospheric showers, CTA's ultra-fast cameras capable of capturing nanosecond flashes will reconstruct each particle cascade in 3 dimensions, letting us trace their paths back through intergalactic magnetic fields like cosmic breadcrumbs. Then there's POEMMA, the probe of extreme multi-messenger astrophysics, which turns the entire concept of ground-based astronomy upside down literally. This proposed fleet of satellites won't look down at Earth or up at stars, it'll peer sideways through the atmospheric limb, treating our planet's edge as a giant fluorescent screen. When an ultra-high-energy cosmic ray strikes the upper atmosphere, POEMMA's ultraviolet eyes will capture the faint glow spreading across hundreds of kilometers, measuring energies beyond what any ground array can detect. Imagine trying to study a waterfall by catching individual droplets versus seeing the entire cascade. That's the leap this technology represents. Together, these projects could finally crack the century-old puzzle of where cosmic rays get their extreme energies, potentially pinpointing individual galaxies or even specific black hole jets as particle accelerators. But the real game changer might come from an entirely new approach: neutrino cosmic ray coincidences. Projects like the Giant Radio Array for Neutrino Detection, or GRAND, aim to catch both particles arriving simultaneously from the same cosmic catastrophe. Since neutrinos travel straight through magnetic fields while cosmic rays curve, spotting them together would be like getting a cosmic voicemail and its return address simultaneously. This multi-messenger technique could unveil dark matter annihilation signals hidden in the noise, perhaps even catching WIMPs in the act of decaying into particle pairs we can actually detect. The most tantalizing possibilities lie in what we can't yet predict. History shows every leap in cosmic ray detection, from cloud chambers to gamma-ray satellites, has revealed phenomena nobody anticipated. As these new observatories come online, they might uncover particle types beyond the standard model, catch echoes of quantum gravity in ultra-high-energy collisions, or even stumble upon messages encoded in cosmic ray patterns. One thing's certain: the universe has been broadcasting its secrets in particles for billions of years. We're finally building the tools to listen. What if the very particles streaking through your brain right now, cosmic rays from distant supernova and black holes, are subtly shaping your thoughts? It sounds like science fiction, but a small group of researchers has dared to ask whether these invisible interstellar bullets might influence human consciousness. The idea, often dubbed cosmic ray consciousness, suggests that random particle strikes in our neural circuits could occasionally alter brain function, sparking creative insights, triggering déjà vu, or even contributing to mental health fluctuations. At its core, the hypothesis leans on two controversial pillars. First, cosmic rays generate cascades of secondary particles when they hit Earth's atmosphere, including muons, which penetrate deep underground and through human tissue. Studies show a single muon can deposit enough energy to disrupt a handful of neurons, roughly equivalent to the electrical activity of a fleeting thought. Second, the brain's sensitivity to tiny perturbations is well documented. Epileptic seizures, for instance, stem from sudden, abnormal neural firing patterns. Could cosmic rays, however rarely, act as cosmic dice rolls, rewiring a neural connection here, amplifying a signal there, just enough to tweak perception or cognition? Skeptics, unsurprisingly, outnumber believers. The biggest hurdle is scale. Your brain endures thousands of muon strikes every hour, yet consciousness remains remarkably stable. Critics argue that neural networks are so redundantly wired and noise-resistant that random particle impacts would drown in the brain's natural electrical chatter. Even if a cosmic ray flipped a neural switch, it's unlikely to rise above the background buzz of neurotransmitters and synaptic noise. Yet a few curious findings keep the debate alive. In 2016, researchers at the University of California, Irvine, exposed rat neurons to radiation levels mimicking cosmic ray exposure during long space missions. The result: subtle but measurable shifts in signal processing, hinting that chronic exposure might cumulatively affect neural function. Another study noted statistical quirks in decision-making experiments during periods of heightened cosmic ray flux, though correlation, as scientists caution, is far from causation. The wildest iterations of this theory venture into philosophical territory. Some speculate that cosmic rays could have played a role in evolutionary leaps. Perhaps a well-timed particle strike nudged an ancient hominid's brain toward abstract thought. Others humorously suggest that sudden creative breakthroughs or light bulb moments might literally involve interstellar intervention. But without rigorous evidence, these remain speculative bedtime stories for the scientifically curious. What makes this idea so tantalizing isn't its plausibility. It's the audacity to ask whether the universe's most energetic phenomena might whisper directly into the human mind. For now, cosmic ray consciousness sits at the fringe, a playful reminder that science thrives not just on answers, but on questions that stretch our imagination to the breaking point. Until someone proves or definitively disproves this cosmic connection, we're left wondering, could there be a grain of truth in the star's silent conversation with our synapses? From the mind-bending "oh my god" particle to the eerie Tunguska event, from pulsar-fueled antimatter factories to the galactic fingerprints hidden in tree rings, our journey through these 25 cosmic ray enigmas reveals one undeniable truth: the universe is far stranger than we ever imagined. Every answer we uncover seems to open 3 new questions. Why do some cosmic rays arrive with energies that defy all known limits? What invisible hands mold their paths across millions of light years? And could these particles hold clues to mysteries we haven't even thought to ask? Consider this: we've mapped the human genome, photographed black holes, and landed robots on Mars, yet a single subatomic particle from deep space can still upend our understanding of physics. The fact that we're routinely surprised by cosmic rays isn't a failure of science, it's proof that we're asking the right questions. Each detection is a thread in a grand cosmic tapestry, woven with forces and phenomena we're only beginning to glimpse. The next chapter of this story is being written right now. Observatories like the Cherenkov Telescope Array are turning the sky into a particle detector, while space-based experiments hunt for antimatter whispers from dark matter collisions. Citizen scientists can even join the hunt through projects like Crayfies, which turns smartphone cameras into miniature cosmic ray detectors. Discovery isn't just for experts in lab coats, it's for anyone curious enough to look up and wonder. So here's my challenge to you: which of these cosmic ray mysteries keeps you awake at night? Is it the eerie positron excess that might be dark matter's calling card? The Fermi bubbles looming over our galaxy like silent giants, or something we didn't even cover, a cosmic wildcard waiting in the data? Drop your thoughts in the comments and let's keep the conversation going. Because the universe isn't done surprising us, and the next big revelation might start with a question from someone just like you. Until then, keep looking up. You never know what invisible marvel might be racing toward us at the speed of